All right, gentlemen, we're gathered here today for an MS Paint certified specialist piezoelectric crystal. He's going to show us about the Aharonov-Bohm effect.
Okay, so this is a solenoid in the middle. You can think of a solenoid as having a uh, a magnetic field running through the center of it, or, or the pole of the magnetic field, I suppose, running through the center of it. Okay, and it's pretty much confined to the interior of the solenoid. You might get some extremely minor levels just outside the coil, but for all intents and purposes, it's confined. Now, if you take let me get another color, like red. If you take a loop, we're gonna, okay, I'm gonna do that. And then we're gonna have a detector. We're gonna just make some little like pink square. It's gonna be the detector. Okay. This is detecting an interference pattern. So what's the interference pattern caused by, you might ask? Well, this loop, you've got oop, you've got electron stream 1 and electron stream 2. Or you could just call it current stream. But anyway, you got current running through these wires, right? And this is all measured out to be perfectly symmetrical. So you know when you send current out through here, it splits open and comes out to the other side. And it arrives, since these two path lengths are the same, it arrives at the exact same time and produces no fringe pattern, right? Okay. So they're aligned perfectly, right? Or at least, I mean, whatever fringe pattern they have, they could just presume that to be what it is. When you power on the solenoid and it produces this magnetic field, let's say that the magnetic field stretches out as far as this. So that's the absolute boundary of the magnetic field. Okay, it doesn't go any further. Okay. Then the magnetic field never touches the red wires, right? There's no magnetic field component to be acting upon the current that's in the wire. So therefore, you can treat the solenoid as if it doesn't exist when you use Maxwell's equations to calculate any type of force imposed upon the charges, upon the electrons as they flow through the wire. The Aharonov-Bohm effect is that even though by means of calculating electric field and by means of calculating magnetic field, you predict zero force, there's no electromotive force at all that you can predict, nothing that would affect charges, right, from either the B field, the magnetic field, or the E field, the electric field. What they find is when they power the solenoid on and it creates this magnetic field that's rotating, um, or that's present, the because it's a solenoid, so there's current running through, so the magnetic field is constantly, moving. The detector detects a change in the interference pattern. There's a fringe shift that happens. Okay, and what it shows is that one loop of the electrons, like one half, has sped up and the other has slowed down. Okay, so this side goes faster and this side goes slower. So one side all of a sudden starts arriving quicker than the other once you power the solenoid on. The only way this can be predicted mathematically is by using the vector A potential, the A field, which is actually fundamental to the B field and the E field. They're both derived from it. Today, in the modern conception of Maxwell's equations, which was largely popularized by Oliver Heaviside et al., they don't use that conception very much at all. They use just the E specific and the B specific component equations. However, you can use the A field, and the Aharonov-Bohm effect is known to demonstrate this. It's known as a quantum quirkiness, quantum weirdness, right, effect. That demonstrates that the A field does appear to be physical in some sense because it's actually causing this effect. Well, what I was going to say is what you could do is you could all of a sudden, instead of only using one loop, you could do another one, and then you could do another one. You could make a bunch of concentric circles of the loops and send electron current through every single one of them and measure the interference pattern at every single one of them. And you could detect the fringe shift in every single loop of a different size and use the force equations to derive the change in the forces in each loop, right? Because it's going to get like diminished more and more the further you go out. And you could acquire the ratios of each loop, right, to each other as they increase in distance from the solenoid. And by doing so, you could theoretically, at least in my mind, you could derive the amount of force being imposed by the A field on each stream of current. And if you can precisely calculate the amount of force being imposed on it by calculating the proportional fringe shifts, you now know the force that the A field imposes, and then you could calculate like the volume of each current stream or the space which it takes up, right? However you want to think of it, however much wire there is how much is the volume, right? Because the entire wire surface is being traversed by the current. And then that will tell you how much ether is in contact with the current. And based on the amount of force spread out over the surface area that it's contacting, that will tell you you could use that to derive. And obviously, also you would have to calculate the velocity, throw the velocity in there, right? But if you know the amount of force imposed, if you know the velocity composed, and if you know the surface area across which, or the volume, the space across which that velocity is, or that force is being imposed, you could use this theoretically to calculate like the mass involved, the theoretical mass involved, right? Because you'd be able to do it in terms of momentum based on the work performed on the charges, and thus you could derive uh, the density of the ether. So this would be a way to derive ether density physically using like electromotive forces.
I like it.
You need a pretty precise lab setup though to do it. And you got a funding barrier there unless you get somebody to grant you that grant, and I highly doubt anyone's going to do that. But maybe if you wrote it up well enough, you could say the density of the
Of the quark,
quantum the 0 point field, the density of the 0 point energy field. Yeah, the energy density of the 0 point field.
the non-density of the 0 point non-physical, definitely abstract mathematical field.
Yeah, but that's my idea, and you already know I got another one. I got other ones.
No, I like it. That's a good one. I
driving
like that one.
density.
I like that.
Yeah,
It would
I
be.
still want to do the one with lasers though.
I would want to do a Dufour and Prunet experiment, but then like see how high you could, or see how far you could separate the two platforms before you like lose the full velocity component to see if that's an effect.
Dufour Prunet, is that the building like shooting down thing?
No, that was where they had a rotating interferometer table and a stationary one with 45-degree angled mirrors, and they were rotating one table underneath the stationary one.
Yeah.
I wonder if you that the fringe was directly proportional, but they were separated by only 4 centimeters from one another. Yeah. Oh, dude, you didn't hear about this one?
Oh, they were just reconfirming George Sanyak.
Well, yeah, but it's a
We're
little
gonna
bit
send you.
worse than that because they had the source in the recorder fixed to the lab wall.
Oh yeah, they were in the recorder and the source were in the lab frame, and the Sagnac table was in its own rotating frame. And they're
Right.
saying that rotation is absolute. It's like, okay, but why in the stationary lab frame am I taking the measurement and seeing the fringe?
Yeah, the classic, dude.
Yeah.
The classic
How did they?
unanswered.
Yeah, what did they steel man it with though?
Uh, Paul Langevin came in and did a Lorentz transfer, well, did a cylindrical coordinate system transformation using general relativity and
About
saying
the
that,
center of the rotation?
yeah, yeah, and then said that, the acceleration of the, rotation is equivalent to gravitation. So therefore it falls under the realm of general relativity. And we have to use the central frame because we're dealing with gravity and gravity pulls you towards the center.
Central frame?
I'm so yeah, the ficticious
The place
convenient
where the
frame,
measurement was never taken?
right? The old fictitious frame
Oh,
where
okay.
the measurement wasn't taken exactly. But he says that because they're dealing with
Okay.
rotation, they absolutely have to. But that's not even fair because the observer is physically not located on that at all. So like, why would you do that
Right.
unless you're just assigning imaginary vectors to space?
Where electromagnetic processes once took place. Yeah, I mean, dude,
Yeah.
to say that anything that's rotating, the only valid frame is the frame right in the center of everything rotating. Um, well, first of all, that's stupid. But second of all, that would mean the only valid frame on for them on Earth would be the center of the Earth. Can't calculate forces on the surface. You got to go to the center.
Ooh, that's actually exactly how they explain Michelson, Gale, Pearson, and Sagnac through GPS and all that. They take the reference frame with respect to the center of the ball.
Oh, I know,
Oh,
but it's
okay,
the same
yeah,
thing as Sagnac's table
right,
because the measurement's not taken in there. If it's
exactly.
only valid there, then how am I getting a directly proportional measurement somewhere else?
Bro, and how about this? If you're an inertial observer, you measure C as C. So if you're at the center of ball, would you even see an observer measuring a different speed? They don't
Hmm.
even know. They don't even
Oh my
know.
gosh,
Ron Hatch goes
dude! I
over that in
just
his book. He cites a bunch of relativity lads attempting to explain it by scoffing and calling me a sodomite. I didn't call you a sodomite. I just thought it with my mind.
Jeez, that's hilarious. Well, I mean, calling you a sod, I mean, that's not a false statement. You literally have it in your
Self-proclaimed
bio.
says he puts the
Yeah,
G in LBGT or whatever. So I don't know.
yeah,
Are are you not a
yeah. I
sodomite
mean,
then? I don't know.
why does he take offense to that? Because I mean, it's like, is that not a nice word? Like, it's just a very specific descriptor.
Yeah.
I mean,
Well, you know what they say, Piezo. Tomato, tomato.
it's like calling